Hello, Mindbenders, and welcome to the very edge of reality. Today, we're not just dipping our toes into strange science, we are taking a running leap into the deepest, most baffling rabbit hole in all of physics. We're going to talk about an experiment so bizarre, so counterintuitive, that it forces us to question the very flow of time itself. Forget what you learned in school about cause and effect, about the past being fixed and the future being unwritten. The experiment we're exploring today suggests something far stranger, that your very act of observation, the simple act of looking at something, doesn't just affect the present moment. It can ripple backward through time and literally rewrite events that have already happened. This isn't a thought experiment from a science fiction novel. This is a real, repeatable, laboratory-verified phenomenon that has left physicists both stunned and fascinated for decades. It implies that the universe might not have a single concrete history. Instead, the past might be a shimmering, probabilistic fog that only solidifies into a definite story once we, in the future, decide to look at it. Now, our everyday experience screams that this is impossible. We live in a world governed by a strict linear timeline. You drop a glass, it shatters. The sound of thunder arrives, the lightning flashes. This is the fundamental law of cause and effect, the bedrock of our sanity and our entire understanding of the physical world. The cause always precedes the effect. It's a one-way street. But what if it isn't? What if, on the quantum level, that street has roundabouts, U-turns, and strange detours that defy our classical intuition? Imagine being a detective arriving at a crime scene. Your presence, your questions, your investigation, it all affects what happens. Witnesses might change their stories, suspects might get nervous. But what if your arrival at the scene on Tuesday could somehow change whether the window was broken or not during the crime on Monday? That's the level of weirdness we're talking about. The concept has a name that sounds like it was lifted straight from a paradox-fueled blockbuster: retrocausality, or backwards-in-time causation. To even begin to grasp this, we have to accept the first rule of the quantum club. Particles like photons and electrons lead a double life. When no one is looking, they behave like waves, spreading out in a field of possibilities, able to be in multiple places at once. But the moment you try to measure one, to pin it down and ask, "Where are you?" it instantly collapses from a wave of potential into a single, definite particle in a single, definite location. This is the famous observer effect. But the experiment we're tackling today takes this a giant leap further. It asks a terrifyingly simple question. What if the decision to observe or not to observe is made when the particle's journey is supposedly over? What if the choice to look is delayed? Does the particle somehow know in its past that it was observed in its future? The answer, unbelievably, seems to be yes. It suggests that information isn't just a passive record of what happened, but an active ingredient in shaping what happens, even retroactively. So prepare to have your assumptions shattered. Buckle up as we journey into the heart of the quantum world, a place where the past is not what it seems, and your gaze might be more powerful than you could ever imagine. This is where physics gets weird, and the universe reveals its truly mind-bending nature. All right, let's pull back the curtain on this master illusionist of physics, the delayed choice quantum eraser experiment. To understand its magic trick, we first need to understand its predecessor, the famous double-slit experiment. It's the quintessential demonstration of quantum weirdness. You fire single particles, like photons, at a barrier with two vertical slits in it. Behind the barrier is a detector screen. If the photons were just tiny baseballs, you'd expect to see two distinct bands on the screen corresponding to the two slits. But that's not what happens when you aren't watching which slit they go through. Instead, you get an interference pattern, a series of many bands, like ripples in a pond. This proves each unobserved photon acted like a wave, passing through slits simultaneously and interfering with itself. But here's the kicker. If you place a detector at the slits to see which one the photon goes through, the interference pattern vanishes. The very act of measuring it forces the photon to choose a path, and it behaves like a particle, creating just two bands. This is wave-particle duality in action. Its behavior depends on whether you know its path. The delayed choice quantum eraser takes this concept and cranks the weirdness up to 11. It was designed to test an idea by the brilliant physicist John Wheeler, who asked, what if we decide whether to measure the path the photon has already passed the slits and should have already decided to be a wave or a particle? The experimental setup is ingenious, but the core idea is what matters. It starts with a special crystal that uses a process called spontaneous parametric down conversion. This crystal takes one high-energy photon and splits it into two lower-energy, entangled photons. Let's call them photon A and photon B. Entanglement is a quantum connection, a spooky action at a distance, where the two photons are linked. Measuring a property of one instantly influences the corresponding property of the other, no matter how far apart they are. Here's the setup. Photon A, the signal photon, is sent directly towards a double-slit barrier and then to a primary detector, D0. Its journey is short and direct. Meanwhile, its entangled twin, photon B, the idler photon, is sent on a much longer path to a completely different area with a complex arrangement of beam splitters and detectors. This is where the choice is made. The path for photon B is set up so that by detecting it in different ways, we can either learn which slit its twin, photon A, went through, or we can erase that information. Some detectors for photon B will tell us the which path information for photon A. Other detectors are configured with what's called a quantum eraser, a beam splitter that scrambles the paths of photon B, making it fundamentally impossible to know which slit photon A went through. The crucial part is this. Photon B's journey is longer, so it is detected when photon A has already hit the screen D0 and completed its journey. The choice to know or erase the path information is made in the future, relative to the event we're trying to influence in the past. So, what happens? Scientists run the experiment, collecting all the data from all the detectors. At first, if you just look at the raw data from the main detector, D0, where photon A landed, you see a meaningless, fuzzy blob, no pattern at all. But then comes the magic. They sort the arrival data of photon A based on knowing the choice made in the future. When they look only at the photon A arrivals whose twins landed on a detector that erased the which path information, they see a particle pattern, two distinct clumps. It's as if those photons knew their paths were being recorded in the future, so they behaved like particles in the past. But when they look at the photon A arrivals whose twins landed on a detector that told the which path information, they see a clear, beautiful wave-like interference pattern. These photons behaved as if they went through both slits at once, because in the future, the information about their path would be unknowable. The pattern at D0, an event in the past, is determined by a choice made at another detector, an event in the future. The past, it seems, remains undecided, a ghostly superposition of possibilities until a measurement in the future collapses it into a single concrete history. This doesn't mean you can send a message to your past self to buy a winning lottery ticket. The patterns only emerge after we correlate the data from both sets of detectors, so we can't know the outcome in advance. But it shatters our simple linear view of time and causality. It suggests that the past and future are intertwined in a way we're only just beginning to comprehend. The universe doesn't decide what happened until it absolutely has to, holding its cards until the very last measurement is made. So, does your observation, your quest for knowledge, literally reach back in time and change what has already occurred? Tell us in the comments what you think. Subscribe for more mind-bending science, and we'll see you in the next one.